So that's a quick overview on how to calculate by hand the correlation coefficient, which you won't do. You'll never do by hand, but at least you have some sense of what it's doing. Couple things to notice. You can't use the word correlation unless you're talking about two quantitative variables and the association between them is linear. And you know it's linear because you have to sort of look at the graph and just use your judgment. Okay, if it looks like a curved association, you're not going to use the word correlation, and you're not going to calculate the correlation coefficient as having any meaning. Okay, this is only something that applies to linear relationships. So when you're looking at a scatter plot, you want to ask these questions. Are the data quantitative? You wouldn't be looking at a scatter plot if they weren't. Is the scatter plot straight enough, meaning is it appropriate to use the word linear to describe the relationship? And are there any outliers? Because outliers can cause the correlation coefficient to really change in a way that kind of may misrepresent the overall pattern. So in computing the correlation coefficient on your calculator, the first thing you're going to need to do for most calculators is you're going to have to go and turn the diagnostic on. So I'll do that in a second here and show you what that means. Okay, so the first button you're going to want to push is the second button. So I'm going to just write the buttons down here. Second. And then you're going to hit the button where you're going to hit 0. So get to catalog. Okay, then you're going to go down to where it says diagnostic on. Okay, diagnostic on. So you have to scroll a little bit. It's in alphabetical order, and there's no search function. So you find diagnostic on, you press enter. Okay. Now it doesn't look like it's done anything. It just says done. But once you've done that, now you can actually calculate the correlation coefficient. So let's do an example. So what we're going to do is we're going to put I'm just going to make a table of just random values, just no context, just to give you an idea of how we do this. So in L1, and I'll show you how to get there in a second. In L1, I'm just going to put these numbers, 1, 2, 3, 5, 6. And I'm going to put in L2, 10, 12, 16, 19, and 22. All right, so again, just hit seconds, and hit stat, go to edit, and go into L1 and put those numbers in. So you can pause the video and do that. Once you've done that, make sure you go to this quit screen, or the blank screen, and then you hit stat. So I'm going to hit stat. You're going to go over to calculate. You're going to go down to linear regression, or linear lin reg. So a plus bx is what it looks like. Okay. Now when you do that, it's going to depend on the calculator you have. Mine looks like it requests an X list and a Y list. You do want to make sure that L1 and L2 are your X list and Y list. Otherwise, you'd have to list that as a comma. So you'd put L1, comma L2. All right. And there is a way to store this into the equation, into the function equation, so that you can just graph it. But we don't want to graph it, because what it's going to do is it's going to calculate a line. But for now, we're just interested in the R value. So in our case, the R value is 0.9901. Okay. Now that is a very strong positive correlation. Okay, again, I made these numbers up, but I mean that if you were to plot those points, you'd see that the relationship's very linear, and R value being close to 1 means that that the relationship is very strong and positive. Okay, so we could say there's a very strong positive correlation. A couple key facts you want to get straight about the correlation coefficient. The sign of the correlation gives the direction. All right, so a positive correlation means that you have an increasing relationship, and a negative correlation indicates that your scatter plot is basically decreasing, top left to bottom right. It doesn't matter which variable is x and which is y, the correlation will always be the same, meaning if you decide to switch the response variable and the explanatory variable, the x and y axes, and then do the correlation coefficient, you'll get the same exact number either way. Correlation is a value between -1 and 1 is something I missed. -1 and 1, of course. -1 being a perfectly negative linear association, and 1 being a perfectly positive linear association. Correlation has no units because in calculating it we found z-scores which have no units. Changing the scale doesn't affect the correlation. It only measures linear relationships. And if the association is linear, the correlation tells the strength and direction, but of course only if it's linear. And it's very sensitive to outliers, so one outlier can cause the correlation coefficient to change. So here's a quick exercise. There's a mistake in each of these sentences, and let's see if we can find what they are. So this first one says, there is a high correlation between the sex of American workers and their income. So see if you can see what's wrong with that based on what's given above. Well, the issue here is that sex of American workers is not a quantitative variable, and correlation only measures the relationship between quantitative variables, between two quantitative variables. We found a high correlation, R equals 1.09, between students' ratings of faculty teaching and ratings made by other faculty members. Well, in this case, we are measuring the relationship between two quantitative variables, students' ratings of faculty teaching and the ratings by other faculty members is certainly something that can be considered quantitative. The problem is that R can't be greater than 1, okay? R can't be greater than 1. So there's a problem. Number 3, the correlation between planting rate and yield of corn was 0.23 bushels. The issue here is that the correlation coefficient is unitless. Okay, so the correlation coefficient is unitless. So you wouldn't say it's 0.23 bushels, you just say it's 0.23.